Okay, so coming back to our dislocation and slips, we are talking about resolved shear stress. Over here, as we indicated in the previous class, this denotes the normal to this plane whose area and the area here is A, therefore, this area will become A by cos phi, and if the force in this direction is F and this is the slip direction, then the resolved force in this direction would become F cos lambda, and therefore, you can see that tau equal to which is equal to F by A, which is shear stress, will become F by A cos phi cos lambda, and therefore, this F by A, which we have already used the term sigma for it. So, as if you are applying a stress sigma on, and remember this is a single crystal. So, you are applying a stress sigma onto this single crystal. So, tau is equal to sigma cos phi cos lambda. Now, this is the tau or the resolved shear stress which is acting on this dislocation along the slip direction. So, this much we have established yet so far. Now, let us say that there is some critical value of this shear stress, resolved shear stress. Okay, what do we mean by critical value of resolved stress? Meaning, even though you are applying the stress, the force here and the normal stress sigma, which comes down to as tau over here, but there is certain value beyond which the dislocation will start to move. So, let us term it as tau CRSS, critically resolved shear stress. So, your tau, this tau which we have obtained here, which can be termed as tau resolved shear stress, equal to sigma cos phi cos lambda, this must be greater than tau CRSS for dislocation to move. Okay, so, this we must know what this value tau CRSS, and this tau CRSS value is something like a fundamental property for a given slip system. So, you would know, and from there you should be able to find out. So, there will be several planes, for each of them you will find the resolved shear stress, and whichever comes out greater than tau CRSS, they will be over there you will be able to see, or you should expect the dislocation would start to move. Or in other words, we can say that if you keep increasing stress, so this direction you are applying force or on a particular area, so which is equivalent to applying a stress. So, if you keep increasing the stress, then the one plane on which the resolved shear stress exceeds the critical resolved shear stress value first will start to slip, and which particular one will start to slip or which will get activated first will depend on the orientation of this crystal. So, you will also need to know the orientation of the crystal. So, orientation of the crystal will help you understand, given the sigma value, what will be the tau RSS, and from that you would compare for all the different sets of possible slip planes, slip systems, and whichever exceeds the tau CRSS first will start to slip or will get activated. So, this is important quantity tau CRSS, and what is it? It is the critical value of resolved stress, but when you look at it and you look at the term critical value of stress, you would be, it would sound similar to something we have already introduced, and what is that? It is the tau PN, the Pearl-Navarro stress. So, what is the relation between tau Pn, which is the Pearl-Navarro stress, and tau CRSS. Remember what were these quantities? Both of them reflect minimum stress to overcome lattice resistance. So, in this sense it looks like both of them are same. And we are talking about the resolved shear stress, that we must keep in mind. So, I will put this in braces here. But there is one major difference here. Tau Pn is a theoretical quantity. You saw that we had a relation that was obtained by Pearl and Navarro. So, tau Pn is a theoretical quantity. And what about tau CRSS? Tau CRSS, as you would imagine, is an experimental quantity. So, from experiment you get to know what is the critical resolved shear stress for a particular slip system. There is one more big difference between tau Pn and tau CRSS. Tau Pn, that the one that has been evaluated, is usually evaluated at 0 Kelvin. On the other hand, tau CRSS, since it is experimental quantity, it is temperature dependent, which whatever temperature you are doing the experiment, it gives you the resolved shear, minimum resolved shear stress for that particular temperature. So, tau CRSS is for a given temperature. So, you can see that we started with tau Pn, we found out different slip system, and then from there we said that in a single system, if you are talking about a single crystal, you apply stress, and then there we inherently invoke the term critical resolved shear stress, which will need to be overcome by the resolved shear stress for dislocation to slip. And so, this was an experimental quantity, while this one tau Pn was a theoretical quantity, but both of them represent the same concept, which is the lattice resistance. So, in order to overcome lattice resistance, there has to be a stress applied, which is represented by tau Pn and tau CRSS. Now, I showed you that there will be particular orientation, and for that particular orientation you will get to have several slip systems, and of these several systems, one of them which will first achieve the critical resolved shear stress, it will get activated. So, let us solve an example based on that. So, let us move on to an example for this tau CRSS. So, what is the question? It is given that for a given single crystal, remember we are talking about, when we are talking about critical resolved stress, the derivation we had, we are using a single crystal. For a given single crystal BCC, and it is given what type of system it is. Why do you need that? Because we need to know what different slip systems can get activated with orientation bar 2, 3, 4. So, the orientation of the single crystal is given, and what is given is the tau CRSS, which is equal to 10 MPa. And since BCC, if you remember, we had more than one type of slip system. So, we are defining which particular slip system this CRSS value is. It is given that it is for when you have 111 direction and 110 plane, for 110, 111, 110 slip system. Now, you have to find which slip plane and direction will get activated first. Okay. So, let us understand the geometry first and then we will explain what this problem is, what this is asking. So, as in the derivation we have a single crystal, we will assume it is a cylindrical bar something like this, and over here there is there will be several planes, we will talk about it more when we start solving it. Let us draw one particular plane. So, this is one particular plane which has the normal like this and this is the central axis. So, with this central axis this is making angle phi as we said earlier, and there is a dislocation line somewhere over here, and for this dislocation line let us say this is the slip direction. So, for this slip direction there is angle lambda. So, phi and lambda we are denoting it by phi and lambda, but this is the bar 2 3 4 orientation, which means that this particular orientation is bar 2 3 4. So, this is the orientation bar 2 3 4 and let us assume that there is some stress being applied, let us denote it by sigma. Let us say this is the slip plane on which gets activated first, then it would mean at certain value of sigma. So, it would mean that this is the sigma required for yielding of the material. So, we can also call it sigma yield. So, it is being increased and at a particular value this starts to get slipping, or it starts dislocations start to move. So, at that particular stress that sigma becomes sigma yield stress, and the value at which it starts to move, it has to be related like we showed earlier, it is related to the critical resolved shear stress. Cos phi by cos lambda. So, if this is the one plane that gets activated first, it means that for this the stress requirement was lowest. It is you keep increasing and at this particular value this achieved the critical resolved shear stress on the plane first, meaning this had the requirement for this was the lowest, and therefore, this must be a this must be smallest quantity, and for that this is a smallest quantity, which means this, which is also called a Schmidt factor, must be largest, but compared to what, we will look at it in a moment. So, for this to be lowest, this also is lower, this particular quantity which I will now circle in red, this must be largest. So, what we are saying is that cos phi cos lambda must be largest. But what are we comparing? We will come to that in a moment. So, our slip system is 111 110. So, now this is a general class of slip system given to you. It is not given which particular plane, it can be 110, it can be 1 bar 10, it can be bar 110. So, that is what you need to find out to get the different values of cos phi and lambda. For example, it could be as well bar 1 1 1 1 0. This could be one particular slip system, and remember, for it to be a slip system, this particular direction must lie on this plane. So, the dot product between these two also has to be 0, and at the same time, so it cannot be all the combination of 111 into all the combination of 110, only those combination of 111 and 110 where the dot product will be 0. Why is that so? Because this is a slip system and the slip direction must lie on the slip plane. So, this particular direction must lie on this plane, so that the product must be 0. Okay, so, this is one example of this. There can be several more that we can find, 1 bar 1, again 110 and so on. So, for each of these you will have to find cos phi cos lambda, cos phi cos lambda, and the one which gives you the largest will be the one that will get activated first. So, how do we find cos phi? So, this phi is you already know the bar 1 1 1, which is the orientation or sorry the slip direction. So, this is the bar 1 1, you have to find the angle between this and bar 2 3 4. So, you just take a dot product. So, what you will do is, let us say we are talking about this particular. So, cos phi will be equal to dot product with bar 2 3 4, cos lambda will be equal to 1 1 0 dot product with bar 2 3 4. So, this will be some, you will have to take the square So, this is the denominator term, and in the numerator what you will have is you will multiply this with this, which is minus 1 into minus 2, which is 2, then add it with the second term to multiplication of second two terms, which is 1 into 3 plus 3 plus 1 into 4. So, it will become 4 plus 3 plus 2. So, in this particular case it will become 9 by this quantity. So, this is the cos phi term. Similarly, you will find the cos lambda term, and you have to do it for all the possible planes. So, what are the possible planes? Now, since we are doing it as an example, so let us do all the calculate it for all the possible planes. So, first we will look at what are the possible systems, possible slips. Then we have to find cos phi into cos lambda, which is nothing but, so if we say that a possible slip is HKL direction XYZ plane, then cos phi is HKL dot bar 2 3 4, as we said earlier, and we have to multiply it with cos lambda, which is nothing but you have to take again x y z, whatever is the x y z, dot product with again bar 2 3 4, okay. And then we have to just find the magnitude. We are not interested in the sign, because sign can be changed by taking the opposite direction. So, we are only interested in the magnitude of this product cos phi and cos lambda. And remember, to make it easy, what we will do here is that there was a denominator term here. So, we can call it A, there was a denominator term here B. Since both of them will remain constant, we need not look at the A and B, we will only compare these two products HKL dot bar 2 3 4 and XYZ into bar 2 3 4, will not normalize it, which will, that is, will not divide it by the term which was coming in the denominator. So, now let us look at what are the possible systems. First, let us look at all the possible 1 1 1 direction. For all the 1 1 1 direction, what are the planes onto which it can be contained? One is 0 bar 1, then we have bar 1 1 0, then we have bar 1 0 1. So, these are all the possible planes on which this 1 1 1 direction can be 1 1 1 slip direction can be contained. So, this takes care of 3 systems. This is not all, we will go to other systems, but first let us find out the cos phi and the cos lambda term. So, you can see here you have to multiply it 1 with minus 2, 1 with 3, 1 with 4 and add these. So, 4 plus 3 minus 2, this becomes 5, and you do the same thing over here 0 bar 1. So, you replace x y z by 0 1 bar 1 and do the dot product. So, you have to just, this one gets nullified 0, and this is 1 3 3 into 1 3, 4 into -1 -4. So, the net is -1 and therefore, this is equal to 5, but we are interested only in magnitude. So, it comes out 5. So, you have to do the same thing. Now, I will just show you the different planes and give you the final values. You can cross check it on your own. So, this for the second one it will come out to 5 into 5 equal to 25. For this third one it will come out to 5 into 6 equal to 30. So, this is all the 1 1 1. Now, let us look at another possible one, which is bar 1 1 1. Now, what are the planes that can contain it? 1 1 0, 1 0 1, and you can check for yourself. These are the only possibilities. We do not have any other possibilities here. And how do I find whether this is contained, the particular direction is contained on a plane? I again do a dot product here, this dot product should be 0. So, that is how I find out. Once I take bar 1 1 1, I take all the possible combinations of 1 1 0, which will give a dot product of 0. So, that is the way to find out this part. And once you have this, also remember that the negatives are possible. So, but we are only interested in magnitude, because we want the largest magnitude. So, we need not worry about the negatives and the positives. So, these are the 3 possibilities over here, and what you will see, it will come out to 9 into 1, 9 into 2, and again 9 into 1. So, this comes out to 9, 18 and 9. So, this takes care of these 2 different. So, this another set of bar 1 1 direction. Now, we will go to third type of 1 1 1 direction, which is 1 bar 1 1, and the possible planes are listed here. So, again I will just note down the So, now at this point you have to ask yourself how many possible 1 1 1 directions are, and the answer would be 4 different types of 1 1 1 are possible, and we have listed 3 here. So, there is one more possible 1 1 1 system, and that is 1 1 bar 1, and the planes which can contain it are 0 1 1, 1 1 bar 1, 1 0 1, 1 1 bar 1 and 1 bar 1 0. So, now that takes care of the last set of planes possible, and the product for this would be -3 into 7. I am not showing you, I am not going through the same steps. I have explained the steps for the first 3, and you can keep applying it over here. So, this is all the possible planes that we have looked at. Now, look at the value. Now, we will start to compare which one has the highest value. So, here the highest one is 21, and if you go over here, what you see is this particular system gives the maximum value 30, which means that when if you were to calculate sigma yield strength by tau CRSS by cos phi cos lambda, this particular plane, which is, if you go back, the plane which gives you the highest one is 1 1 1 bar 1 0 1. So, for this it came out to be 30, and there was in denominator you have A and B. What are those denominator A and B which we had showed earlier? This is nothing but these 2 terms. This will become A, this will become B. But we are not interested in finding out the sigma yield strength value, but you can see that once you know what is the tau CRSS and we have already calculated which particular plane to select, and we can find A and B. So, you will be able to find cos phi cos lambda for this. So, it will be 30 by AB, and you can substitute it over here to find what will be the yield strength. In fact, for this particular system you would be able to show that the yield strength would come out to approximately 20 megapascal. But our problem was only to find which particular slip system will get activated, which means our answer is just we have to just calculate, or we have to just show this up to this part. So, we have, as long as we have showed that this is the largest value, we are done, we do not need anything more. I am just showing you that there can be additional step that you can do, and also calculate the yield strength value or the stress value at which this slipping will occur on this particular plane. So, there will be several number of planes. So, if I could let me try to now visualize what I have just explained. So, there were several of these 111 direction, 101 planes. So, there are several of these 111 planes. For each of them there will be a different, the tau CRSS is constant for all of these. Tau CRSS is same for all of these, but tau RSS one for this tau RSS 2 for this tau RSS 3. So, all of them will have different resolved shear stress, and the one which is the smallest will reach the tau CRSS first, because we keep increasing the stress value, or even if you are not increasing, but what it is showing is that this particular one will be able to get activated on application of stress the earliest, and therefore, that particular slip system, let us say it is tau RSS 3, then this particular slip system gets activated. So, that is the purpose of using or going through this exercise, to be able to identify in a single crystal system which one will start to deform. So, here the dislocations will start to move, and it leads to rotation of the crystal, which we will look at more when we get to the plasticity part. So, it will lead to the rotation of the crystal, and slowly when the rotation becomes such that some other plane gets activated. So, there are different stages of deformation in a single crystal. First, there is one particular slip system gets activated, then multiple slip systems get activated, and then entanglement of these dislocations leads to further hardening of the material. We will talk about these later on at the later stages when we talk about the plasticity part. So, for now what we need to do, or we at this stage what we want is to understand, this is for single crystal, what about polycrystals. So, this is a question I will leave you with. So, I have showed you here for what happens in a single crystal. Think what will happen, what will be the scenario when you have a polycrystal, which is what most of the materials or metals and alloys are. So, I will leave you with that thought, and we will come back to this in the next lecture.